Okay. Now suppose I am choosing an examples where my vector space V is P2R and we are considering a polynomial fx which is given by 4 plus 6x minus 7x square. Can you tell me what will be the coordinate vector of f with respect to this basis beta, where beta is basis of P2R? What will be the value of this? Can you tell me? Those who have not written their student IDs in the chat box, please do so quickly. Okay, can you tell me what will be the answer to this particular problem?
So what is the basis here?
Tell me. You have to tell
The
it.
Okay, sir. Okay, sir. Just a minute.
Yes.
X square x and 1.
Basis?
Basis is x square x and 1.
But say it in a reverse order. Don't say it in a descending order.
1
You are,
x and x.
yeah.
1x
This is
x square.
yes. Maintain the sequence. So it is 1x x square. This is the basis.
Minus 7.
Bolo?
Sir,
So
4,
what-
6 minus 7.
Yeah, 4, 6 minus 7. Because you see, it is very simple. Because you see, 4 plus 6x plus minus 7x square can be written as 4 into 1 plus 6 into x minus 7 into x square. So 4, 6 minus 7, these are the scalars over here. And we consider these scalars column wise to represent the coordinate vector of f with respect to this basis beta. Okay, so this is the answer to the given problem. It is very simple. We shall now generalize the definition of the coordinate vector of x relative to beta. Now we are going to generalize it to the representation of the linear transformation with respect to the basis beta. So let us generalize the definition a little bit further. Okay. Now suppose beta is equal to v1 comma v2 vn, and gamma is equal to w1 comma w2 wm, be two ordered bases of two finite dimensional vector spaces, V and W respectively. Suppose this we have in our knowledge, and let us consider a linear transformation which is defined from V to W. Then for each index j lying between 1 to n, there exist unique scalars aij belonging to f, where the index I runs from 1 to m, such that we can define the linear combination as the following. You take any vector from the basis beta, we apply the linear transformation on the basis vector. You know that j is running from 1 to up to n, and you see there are n basis vectors over here. See the index. this can be expressed as a linear combination as the following: Aij, Wi, see the index of W, the last index is M. So here the variable is I, which will run from 1 to up to M. We can always express this in the following manner. And using the notation, we call the M cross N matrix A, we call N cross M matrix A defined by Aij is equal to Aij. The matrix representation of the linear operator T in the ordered basis, beta and
Sir,
gamma. And yes, tell me, where A
sir, I have
is,
not understood this. Suppose, money, but I have
Hello?
not understood.
You will understood when you will just write the definition. I'm going to give you an example. If I do not do the example, you will not understand what it is written over here, because you will be lost in the notations and symbols over here. You will, once I discuss the problem, you are going to definitely understand what I am talking about. And you just go back to the definition. Then after doing the problem, you come back to this definition. You will understand what I am talking about. Now, first of all, because it is officially I have to define the thing first of all, before I move on to the discussion of the problem. So I'm giving you this definition, but I am also pretty sure that you will not be understanding anything from the definition, the statement of the definition itself, because when I was student, I was also facing the same sort of problem. But once I give the example to you, you will automatically understand what I am talking about. So I am going to the next page. I will again come back to this page. If you are not here, if you have not copied it yet, or you have not taken the screenshot, don't worry. I'll again come back to this particular page. I will try to show you.
But in the second
Yes.
In the second last line, what you have written and using the notation we
call the M cross N matrix A defined by this, the matrix representation of T, where it is written as A equal to T beta gamma.
Okay, sir.
Now
Okay,
I'm going
sir.
to let you understand what do we mean by this actually. And once I solve this problem, you will tell me that whether you have understood this or not. Okay, this is my example. I am choosing two vector spaces V and W. Try to understand the problem very carefully. My first vector space is R2. V is my R2 and my W is R3. Geometrically, my vector space V is the two-dimensional space and my vector space W is the three-dimensional space. And I am going to define a transformation T from R2 to R3. I'm going to define a transformation from R2 to R3 by this formula. T of A1, A2 is equal to 2A1 minus A2, 3A1 plus 4A2, A1. Okay. Now, can you tell me whether this transformation is linear or not? What is the way out? How do we check whether the transformation is linear or not? What do we do first? What is the definition of checking? What is the way of checking whether this transformation is linear or not? Because first of all, before I move on to the section to find out the matrix representation, I have to justify that it is a linear transformation. So step number one, check whether T is linear. How do we do it? I showed in the last class that one way is to check this one, the Tx, T of x plus y is Tx plus Ty. And you check that T of Cx is equal to C into Tx. You can do it individually, show number 1 and number 2 separately, or another way to check is the following. Consider
Cx plus y.
yeah a1 x1 plus a2 x2 in general sense, an xn. You have to check a1 into tx1 plus a2 into tx2 plus dot 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 plus an into txn. Now I'm going to use which one? The first one, say. Okay, first one is very easy. I am considering two elements x and y in R2. I'm considering two elements x and y in R2 so that x is of the form a1 comma a2, y is of the form b1 comma b2. Now T of x is T of a1 comma a2, and T of a1 comma a2 by definition is this one, twice a1 minus a2, 3a1 plus 4a2 and a1 by definition. T of y is this one, T of b1 comma b2, which is 2b1 minus b2, 3b1 plus 4b2 and b1. And what is x plus y? Now, what is x plus y? X plus y is a1 comma a2 plus b1 comma b2. So we have a1 plus b1 comma a2 plus b2. This is by definition x plus y. What will be T of x plus y? T of x plus y will be T of, is for simplicity, let us consider this to be C1 comma C2, where C1 is A1 plus B1 and C2 is A2 plus B2. So this will be T of C1 comma C2. By definition, this would be T of C1 minus C2, 3C1 minus plus 4C2 and C1. This is by definition. We have this. And now you can resubstitute the values of C1 and C2 over here. So we'll get 2 into A1 plus B1 minus A2 plus B2, comma 3 into A1 plus B1 plus 4 into A2 plus B2, comma A1 plus B1. A1 plus B1. This is what you are going to get by after you've put transformation T on x plus y. Now I'm writing here, if I a little bit simplify it, what will I get? We'll get 2a1 minus a2 plus 2b1 minus b2 from the first one, 3a1 plus 4a2 plus 3b1 plus 4b2 from the second one, and a1 plus b1 from the third one. And we can always separate it in the following manner: 2a1 minus a2, comma 3a1 plus 4a2, comma a1 plus 2b1 minus b2, comma 3b1 plus 4b2, comma b1. And the first one is nothing but T of x. Just look at this. Second one is nothing but T of y. Look at that. and we see that the first property is being verified. So first one is satisfied. Now we are going to see whether T of Cx is equal to C into Tx or not. So can I go to the next page?
Yes, sir.
Please wait a minute.
Okay. So now we are going to see if anybody is missing anything. I will again come back. I will again show you the pages. T of Cx. T of Cx means T of C into A1 comma A2, because X belongs to the space R2, which is nothing but T of CA1 comma CA2, because this is how the scalar multiplication is defined in R2, and which is 2 CA1 minus CA2, because this is the first coordinate and this is the second coordinate, comma 3C1 CA1 plus 4 CA2, comma CA1. This is what I am getting from the definition of the transformation. Now what we can do is the following. We can take C common and we can write it as 2A1 minus A2. We can take C common and we can write it as 3A1 plus 4A2. And we can take C common. C not C is simply C is there, so CA1. And you know that each of these elements are getting multiplied by C, so we can take C outside. We will get C into 2A1 minus A2, 3A1 plus 4A2, and A1. And what is this? This is your T of X. So from number 2 and number 1, we have proved that T is linear transformation from R2 to R3. Okay. Now, once I find that this is the linear transformation, we will try to apply this particular, try to understand what we mean by this particular formalism of matrix representation of the linear transformation. So let us come to this particular point. We have verified that the transformation from R2 to R3 is linear. We know that beta 1 1001 is the standard ordered basis of R2, and beta 2, or rather, if I want to stick to the notations defined in the definition, then let us call this first one as beta and the second one as gamma. Then it will be easy for you to correlate. Gamma is the basis for standard ordered basis for the vector space R3. Standard ordered basis of R3. So now you just look at this definition. We had two vector spaces V and W. We need a linear transformation from V to W. We have found a linear transformation from V to W. We need a basis beta for V. We need a basis gamma for W. So everything has been found over here. And now what they are doing, carefully observe. They are choosing the basis element of the vector space V. They are choosing the basis element of the vector space V, and they are trying to represent this transformation with respect to the linear combination of the basis elements of W. So choosing the basis element from V, basis elements from the basis of V domain they are trying to represent it as a linear combination of the basis elements of the basis of the codomain or range, which I am going to do right now. So in the domain, we have how many basis elements do we have? We have this and this. Now we are going to apply this transformation T. We are going to apply this transformation on this basis element. So we get the following. T on the first basis element of R2, T10. If you call it as V1 and V2, and just call them as W1, W2, W3, if you want to correlate. So T10 can be, by definition, it is what? It is 2 into 1 minus 0, comma, 3 into 1 plus 4 into 0, comma, 1 by the transformation. Because transformation is 2a1 minus a2, 3a1 plus 4a2 and a1. And which is 2, 3, comma 1. This is what we get if we apply the transformation on the basis element. Next element that is present in the basis of, this is my TV, TV1. My TV2 is the following, T of 0, comma 1. What is that? This is 2 into 0 minus 1, 3 into 0 plus 4 into 1, comma 0, which is minus 1, 4, 0. Now, no more basis elements are there, so we have to stop over here. Our next job is to write these images as a linear combination of W1, W2, W3. Some linear combination of W1, W2, W3. It is very easy to find, which is 2 into 1, comma 0, 0, 3 into 0, comma 1, comma 0, and 1 into 0, comma 0, comma 1, which is 2 W1 plus 3 W2 plus 1 W3. The next one is minus 1 into 1, comma 0, comma 0. This is 4 into 0, comma 1, comma 0. And this is 0 into 0, comma 0, comma 1, which is minus 1 into W1 plus 4 into W2 plus 0 into W3. Now just look at what we have found. This, just look at this. I runs from 1 to M. M is the number of basis elements present in gamma. Here I is running from 1 to 3. 3 basis elements are present from in the basis gamma. Now what we are going to do, just carefully observe, just try to break this particular transformation. What you get if I run I, if I take
We
I
get
equal,
Aij.
Aij, so if I take I equal to 1, we get A1j into W1 plus A2j into W2, A3j into W3, A1j, A2j, A3j, A4j. So these things, A1j, A2j, A3j, they will come row wise or column wise. They are coming row wise or column wise.
Row wise.
Row-wise.
No. How? A1j. 1 I stands for row and J stands for column.
Yes, sir. Column wise. because
Column
the
wise
column
is
Column
coming.
wise.
A1j, A2j, A3j, A4j, AMJ. Now you see. So therefore, if I try to apply it, if I try to find out the matrix representation of this, I'm writing in the next page. I do not have space over here. So with respect to beta and gamma, it is not moving. Just a minute. Okay. Now with respect to beta and gamma, therefore, my matrix representation will be 2, 3, 1. This will come in the column. We will write 2, 3, 1. and -1, 4, 0 will go to the next column. -1, 4, 0 in the next column, which is the required matrix representation, which is the required matrix representation, of T with respect to basis beta of R2 and gamma of R3. This is your answer. Now you tell me, someone was telling that I have not understood. Have you understood?
Yes, sir. Now I've understood.
Clear, everybody?
Sir, what was the path after with respect to required matrix representation of T
Yeah,
with respect to?
see. So what this the analysis is saying us, that this particular thing is saying us that if you want to suppose, if you want to find out some sort of transformation, how one particular space is transforming, a two-dimensional space system is being projected to a three-dimensional system, a 2D image. In the year 1992, the movie Terminator Part 2 Judgment Day came. Probably you have seen this particular movie. In the year 1999, Titanic came. And later, in later years, all these movies were made to 3D movies. Judgment Day were also made a 3D movie, and Titanic were also made a 3D movie, and they were, re-released in the theater. So what in a two-dimensional space is actually moving to a three-dimensional space. All the movies that you see on the screen, all the movies are actually the pixelates. Each pixelate is actually a vector. And in two-dimensional space, each pixelate has a coordinate which can be represented as a linear combination of the standard ordered basis 0, 1, and 1, 0 of the screen on which you are seeing the movie. When you are projecting each pixelate to a 3D pixelate, a three-dimensional space, each pixelate of the three-dimensional screen were being represented by the vector 1, 0, 0, 0, 1, 0, 0, 0, 1. And you are seeing the movie with the help of a special spectacle. Now, when you are doing the transformation, that means what? Your 2D screen is being transformed to a 3D screen. And in your 2D screen, there are infinitely many points. In your 3D screen, there are infinitely many points. But this particular theory is saying that you don't have to look at the individual transformation of the points lying on the plane. Just consider the basis elements, look at their transformation, how they are transforming, you will get the taste of the entire thing. That is the logic. That is the motivation behind studying this particular topic, and it is very much required in image processing, and in machine learning also, and in quantum computing also. If you take any quantum computing book, you will find that from there they actually begin their topics. Try to discuss. They do not discuss the definition of vector space. They start from here. Now, if you have understood this particular thing, tell me, I'm giving you another transformation, and I'm declaring that let T be a linear transformation. You don't have to check whether it is a linear transformation or not. That I'm actually, I have already done for you. Say, let T be a linear transformation from Rn to R. R is the set of real number. That is T colon Rn to R defined by T of A1, A2 dot AN, which is A1 plus AN. Okay. Your job is to find T of beta gamma, where beta is basis of Rn and gamma is basis of R. Can you tell me what will be the answer to this problem? Try to do this particular problem. I'm pausing the recording over here. This is your classwork. Less than 1 minute is remaining, so you join in the next session and tell me what is the answer. This is the answer to the problem that I gave you a few minutes ago. Okay, this is the answer. Now you are supposed to give